Hi there, I'm Micaela Kaplan, the ML Evangelist at HumanSignal, and this is In the Loop, the series where we help you stay in the loop with all things data science and AI. Last week on In the Loop, we talked about task-based agreement metrics that you can use to understand the quality of the labels you're getting on a per-task basis. This week, we're going to dive into two metrics that can help you understand how reliable your annotators are from a project or dataset level, Cohen's Kappa and Fleiss Kappa. Let's dive in. We'll start with Cohen's Kappa. Cohen's Kappa, which is credited to Jacob Cohen in 1960, is a metric that measures the reliability of two raters classifying n items into C categories. The formula is kappa equals the observed agreement minus the expected agreement divided by 1 minus the expected agreement. By observed agreement, we mean the proportion of times that the raters agreed on the answer. By expected agreement, we mean the proportion of the time that the raters could have agreed by chance. Let's do an example together. Let's say we have two annotators who each annotated the same 50 samples. We can use this table to see how each annotator has annotated all the samples. Let's calculate the observed agreement, PO, first. This is the number of times both raters said yes, 15, plus the number of times they both said no, 12, divided by the total number of annotations, 50. This gives us an observed agreement of 0.54. Next, we'll calculate the expected probability. We'll do this in two steps. First, we'll calculate the probability of a yes, which is the number of times rater 1 said yes, 15 plus 10 is 25, divided by the total number of annotations, 50, multiplied by the number of times rater 2 said yes, 15 plus 13 equals 28, divided by 50. This gives us a probability of yes of 0.28. Then we'll do the same calculation for the probability of no, as shown on the screen. Finally, we'll add these two numbers together, giving us a chance agreement or an expected probability of 0.50. This could have been anything. It's just this example that we get an expected probability of 50%. Now, to calculate kappa, we'll plug in the numbers that we calculated to the formula. 0.54 minus 0.5 divided by 1 minus 0.5 gives us 0.08. This means we have slight agreement between the two annotators. We'd probably want to retrain them and work towards a higher agreement. Cohen's Kappa works great for two raters, but what if you have more than two? That's where Fleiss Kappa comes in handy. Named after Joseph Fleiss, Fleiss Kappa is an extension of Cohen's Kappa that works with more than two raters, picking between a fixed number of classes. The basic formula for Fleiss Kappa is the same as the one for Cohen's Kappa. The observed probability minus the expected probability divided by 1 minus the expected probability. The difference in Fleiss Kappa is how we calculate the probabilities. You can see them here on the screen. We'll go over them in depth in our example. Note that P bar here is the same as PO in our first example. Let's take a look at an example. Let's say that we have 4 raters who each annotated 7 items as shown below. We'll start with the expected probability in this case. The formula says that the expected probability is the sum over all j of q squared j, where q sub j is the probability of a class j. Essentially, we need to square the probabilities of each class appearing and then sum them. To calculate this, first we need to count up how many yeses and nos we have for each task. We'll do this by filling out a chart. For task 1, there are 3 yeses and 1 no. In task 2, there are 0 yeses and 4 nos, and we can continue this way all the way down the chart as shown on the screen. Then, we sum each column to get the total number of yeses and nos in the dataset. In this case, yes appears 15 times and no appears 13 times. In total, there are 28 ratings, 7 tasks times 4 raters. Next, we can calculate the probability of each class. For yeses, 15 divided by 28 gives us 0.536, and for nos, 13 divided by 28 gives us 0.464. To calculate the expected agreement, all we need to do is square these values and sum them, giving us a total of 0.503. Now, we need to calculate the observed probability. We'll work through this step by step. It's not as bad as it looks in the formula. For the first term, big N is the number of subjects or tasks, and little n is the number of raters. In this case, we have a big N of 7 and a little n of 4, so we can plug these numbers in and calculate the first term, which is, in our case, 1 over 7 times 4 times 4 minus 1, which is 0.012. Next, we can square each value in the table we created to calculate the total yeses and nos, and add them up. In this case, that's 9 plus 1 plus 0 plus 16, all the way over to 9 plus 1 in the last row of the table. The sum of the squares of the table is 86. For the last term, we just get the total number of observations, 7 times 4 equals 28. Now we can plug into the formula as follows. 0.012 times 86 minus 28 equals 0.696. Finally, we calculate Fleiss's Kappa by plugging in the numbers we got for the expected and observed agreement into the formula. 0.696 minus 0.503 divided by 1 minus 0.503 equals 0.388, which is a fair agreement. Again, in this example, we'd probably want to continue to train our annotators to improve their overall agreement relative to chance. Both Cohen's and Fleiss's Kappa are great ways to measure the reliability of your annotators when annotating multiple choice tasks. We can interpret the scores, which range from 0 to 1, using a chart like this one. In today's examples, we demonstrated how to calculate both metrics when raters are asked to choose between two classes, but the theory holds regardless of how many classes you're choosing between. What happens if you're not working with categorical data? What about if you have missing data? In our next In the Loop, we'll wrap up our series on agreement by diving into Krippendorff's alpha, an even more flexible dataset level metric of agreement. That's all for this week. Thanks for staying in the loop. Want even more In the Loop? Check out our other videos. Don't forget to like and subscribe to stay in the loop.